Hello everyone, welcome to VLSI Flow. I am Nagraj Ramawat and this is the part 2 of the Complete Verilog HDL course. In this session, we are going to learn about vectors in Verilog. In the previous part, we discussed the basics of Verilog and single bit signals. Now, in this part, we will move on one step forward and understand how to work with multi-bit signals and which are called vectors. Vectors are very important in digital design because we use them to represent buses, registers, and data paths. I will explain everything in simple and practical way with clear examples so even beginners can understand easily. So let's get started and into vectors in Verilog HDL. Let's quickly look at the course overview for this part of the Verilog HDL course. First, we will start with vectors. Here, you will understand how to declare multi-bit signals and how they are used in real digital designs. Next, we will move to arrays and where we learn how to store multiple values efficiently in Verilog. After that, we will discuss parameter constants and parameters help us write reusable and scalable designs. And we will also see parameter overriding with examples. Then we will cover different types of operators in Verilog. This includes logical operators and bitwise operators, reduction operators, shift operators, and equality operators. We will also learn relational operators and concatenation operators and conditional operators and arithmetical operators. Each topic will explain in simple syntax and clear examples and practical use cases. By the end of this part, you will be confident in using this concept while writing real Verilog code. Now let's understand vectors in Verilog. First, what is a vector? In Verilog, a vector is multi-bit signal. It allows us to group multiple bits together and treat them as a single signal. Vectors are mainly used to represent data buses, counters, addresses, and other multi-bit values in digital designs. In Verilog, vectors are declared using MSB to LSB notation. For example, reg 7-bit and 0-bit data. This means data is an 8-bit register, where bit 7 is the most significant bit and bit 0 is the least significant bit. Similarly, we can see here where 3-bit and 0-bit addresses represent a 4-bit wire. The width of vector is calculated using this formula. Width is equals MSB minus LSB plus 1. Now let's see how to assign values to a vector. A vector can be assigned values in binary, decimal or hexadecimal format. For example, data equaled 8 B10101100. Here we are assigning an 8-bit binary value to the vector data. Finally, we can access individual bits of vector using an index. Data 0-bit refers the least significant bit and data 7-bit refers to the most significant bit. This bit level access very useful when performing control, masking and bitwise operation in Verilog. So vectors help us write efficient and readable and hardware-oriented Verilog code. Now let's move to the next topic, arrays in Verilog. First, what is an array? An array in Verilog is a collection of elements of the same data type and stored under a single name and accessed using an index. Arrays are mainly used to represent memories, lookup tables, and to store multiple data values efficiently. Now let's see the types of arrays in Verilog. There are two main types, one dimensional arrays and multi-dimensional arrays. First one, dimensional arrays. This type of arrays uses singles index. For example, reg is 7-bit, 0-bit. Number is 0, 1, 5. This means we have 16 memories locations from 0 to 15 and each location stores 8-bit data. Next, multi-dimensional arrays. These arrays use more than one index. For example, register 7-bit and 0-bit, matrix X 0, 3 and 0, 3. So this represents 4 by 4 array where each element is 8-bit wide. Finally, let's look at the application of arrays. Arrays are commonly used in RAM and ROM modeling, register files and FIFOs and buffers, and lookup tables in digital designs. Arrays make up Verilog code organized and scalable and closer to real hardware implementation. Now let's move to the next important concept, parameter constants in Verilog. A parameter in Verilog is a constant value used to define a design properties such as width, depth, and size. Once a parameter is defined, its value does not change during simulation. That is why parameters are called compile time constants. Now, why do you use parameters? Parameters help us make our designs flexible and reusable. They allow us to avoid hard-coded values in the code. And most importantly, they make it very easy to change the design size without rewriting the entire code. Let's understand this with an example. Here we have a simple counter of module. We define a parameter called width and set its value to 4. This parameter is then used to define the width of the output register count. So count becomes 4-bit counter. If we want an 8-bit or 16-bit counter, we only need to change the parameter value. The rest of the code remains the same. Inside the always block, on every positive edge of the clock, the counter increments by the 1. And when the reset is active, the counter is cleared to 0. This shows how parameters help us write clean and scalable and professional Verilog code. Parameters are commonly used in memories, buses, and counters, where design size may vary based on requirements. Now, let's understand parameter overriding in Verilog. Parameter overriding means changing the default value of a parameter at the time of module installation. The important point to remember is the module code remains the same, only the parameter value changes. This makes our design highly reusable and flexible. There are two ways to override parameters in Verilog. The first method is name-based parameter overriding. In this method, parameters are overridden using their parameter names, not their position. This is the recommended and safest approach, especially in large designs. For example, we override the parameter width and set it to 8 while installation the counter module. Even though the original module might be written with equal to 4. Here the counter becomes 8-bit counter without modifying the original module code. The second method is order-based parameter overriding. In this approach, parameters values are overridden based on their position in the parameter list. This method works, but it is not preferred because if the parameter orders changes, it can lead to wrong parameter assignments. That's why in real projects and interviews, name-based parameters overriding is always preferred. So the parameters overriding allows us to use the same module with different sizes and configurations, making our Verilog design clean and scalable and professional. Now let's move to operators in Verilog. Starting with logical operators are mainly used to evaluate conditions in Verilog. These operators treat the entire operand as either a true or false, not by bit. The result of logical operations is always a single bit value. If the condition is true, the result is 1. If the condition is false, the result is 0. In some cases, if the result is ambiguous, it can be X, meaning unknown. The three logical operators in Verilog are logical AND is represented by double ampersand, logical OR represented by double vertical bar, and logical NOT is represented by explanation mark. Let's understand this with examples. In the logical AND example, if the inputs A and B are 1, then the result is 1. If any one inputs is 0, the result becomes 0. In the logical OR example, if at least one input is 1, the result is 1. In the logical NOT example, if the input is 0, the output becomes 1. And if the input is 1, the output becomes 0. An important rule to remember is any non-zero value is treated as true and 0 is treated as false. If the input contains X or Z, the result may become unknown. Logical operators are mostly used in if conditions, while loops and control logic in Verilog. Now let's move to the next type of operators called bitwise operators. Bitwise operators perform operations on each individual bit of the operands. Unlike logical operators, which treat the entire value as true or false, bitwise operators work bit by bit. This means each bit of the result is calculated by independently. The main bitwise operators in Verilog are bitwise AND represented by ampersand. Bitwise OR represented by single vertical bar. Bitwise XOR represented by caret. And bitwise NOT represented by tilde. Let's understand with the examples. In the bitwise AND example, each bit of A is ANDed with the corresponding bit of B. For example, A equal to 3B101 and B equal to 3B110. When we apply bitwise AND, the result becomes 3B100. In the bitwise OR operations, if any corresponding bit is 1, the result bit becomes 1. In the bitwise XOR operation, the result bit becomes 1 only when the input bits are different. In the bitwise NOT operation, each bit is inverted, 1 becomes 0 and 0 becomes 1. An important rule to remember is bitwise operators operate bit by bit and output width is the same as the input width. Bitwise operators are widely used in data manipulation, masking, and digital logic circuits. Let's move to the next type of operators uh, called reduction operators. So, reduction operators are unary operators, which means they work on single operand. They operate on all bits of a vector and produce a single bit result. In simple words, reduction operators reduce a multi-bit value into one bit. The commonly used reduction operators in Verilog are reduction AND, reduction OR, reduction XOR, reduction NAND, reduction NOR, reduction XNOR. Let's understand them with examples. In the reduction AND operation, the result is 1 only if all bits of the vector are 1. If even one bit is 0, the result becomes 0. In the reduction OR operation, the result is 1 if at least one bit is 1. In the reduction XOR operation, the result depends on the parity of ones. If there is a even number of ones, the result is 0. If odd, the result is 1. Reduction NAND, NOR and XNOR are simply the inverted versions of the AND, OR and XOR respectively. An important rule to remember is the input is always a multi-bit vector, but the output is always a single bit. Reduction operators are widely used in parity checking, error detection, and status flag generation in digital designs. Uh, let's move to the shift operators in Verilog. Shift operators are used to move the bits of vector either to the left or to the right by the specified number of positions. While shifting, new bits are inserted based on the type of shift operations. Verilog supports four types of shift operators: logical left shift, logical right shift, arithmetic left shift, and arithmetical right shift. Let's start with logical shift operations. Logical shifts are mainly used for unsigned data. In a logical left shift, bits move to the left and the vacated right bits are filled with the 0. For example, if A equals 4B0011 and we perform A left bit 1, the result becomes 4B0110. In a logical right shift, bit move to the right and the vacated left bits are filled with a 0. For example, here we can see A equal to 4, B 1001. A right shift 1 gives 4B0100. Now let's look at the arithmetic shift operations. Arithmetic shift are used for signed data. The important point is in arithmetic right shift, the sign bit is preserved. For example, if B is signed value 4B1100 and we can do B right shift, arithmetic shift 1. The result becomes 4B1110. This preserves the sign and maintains the correct signed value. So to summarize, the logical shifts filled with zeros, and while arithmetic right shift preserves the sign bit, shift operators are commonly used in multiplication or divisions by powers of two data alignment and bit manipulation. Now let's move to the equality operators in Verilog. Equality operators are used to compare two operands and check whether they are equal or not. The comparison is done bit by bit. Verilog provides four types of equality operators. One is logical equality, logical inequality, case equality, and case inequality. First, let's talk about logical equality and inequality. Logical equality is represented by double equals, and logical inequality is represented by not equals. In logical equality, x and z are treated as unknown values. Because of this, the result can be 1, 0 or x. For example, if the values are exactly the same, the result is 1. Next, let's look at the case equality and case inequality. Case equality is represented by triple equals and case inequality is represented by not triple equals. In case equality, x and z are treated as valid values. So the result is always either 1 or 0, never x. This means case equality very useful in test benches and verification, where we need to check the exact bit level matches including x and z. This usual logical equality in normal design comparisons. So and use the case equality when you want to compare x and z explicitly. Equality operators are commonly used in if conditions, assertions, and verification logic. Now let's understand relational operators in Verilog. Relational operators are used to compare the magnitude of two operands. The result of any relational operation is always a single bit value. If the condition is true, the result is 1. If the condition is false, the result is 0. The main relational operators in Verilog are greater than, less than, greater than or equal to, less than or equal to. Let's understand with examples. The greater than example. If A is 6 and B is 3, the condition is A greater than B becomes true. So the output is 1. So in the less than example, if A is 2, B is 5, then A less than B is true and the output is again 1. In the greater than or equal to example, when the both values are equal, the condition is still true. So the result is 1. An important rule to remember is about x and z values. If any operand contains x or z, the result of the relational operation becomes x, which means unknown. Because of this behavior, the relational operators are mainly used with known numeric values, especially in control logic and comparisons. So the relational operators is help us to make decision based on greater than, smaller or equal comparisons in Verilog designs. Now let's move to the concatenation operators in Verilog. Concatenation is used to join multiple bits or vectors together to form one larger vector. In Verilog, concatenation is represented using curly brackets. Let's look at simple concatenation example. Here we have three signals A, B and C. When we write y equal to A, B, C like this, these signals are joined side by side. This important thing to remember is orders matters. The left most value becomes the most significant bits and the right most value becomes the least significant bit. The width of the result is sum of the width of all operands. Now let's talk about the replication operator, which is often used together with concatenation. The replication operator is repeats a value multiple times. The syntax is n times inside curly brackets. For example, if x is 1 and we write is like this for curly brackets x. So the result becomes 1 1 1 1. So we can also use mixed concatenation and replication. In this example, we can repeat like this A twice and then add B and then repeat the least significant bit of C twice. So concatenation operators are very useful in bus formation, data packing and bit manipulation. They help us to write clean and efficient Verilog code. Let's move to the conditional operators in Verilog. The conditional operators is used to select one of two expressions based on a condition. It is also called a ternary operator because it is involves three parts: a condition, a true expression, and a false expression. These are three. The syntax of the conditional operator is condition, true expression, and false expression, like this. Now let's understand how it works. If the condition is true, the true expression is selected. If the condition is false, the false expression is selected. Let's a simple example. Here we have a select a signal called select. If select is 1, the output y takes the value of a. If select is 0, the output of y takes the value of b. So we can understand here this behavior is exactly the same as 2 to 1 multiplexer. In another example, the condition itself is an expression. If the value of c is non-zero, it is treated as true and y takes the value of a. If c is 0, it is treated as false and y takes the value of b. An important rule to remember is any non-zero value is considered true and 0 is considered false. Conditional operators are widely used to write compact combinational logic, especially in mux-based designs. Now let's move to the final type of operators in the section. So called arithmetical operators. Arithmetical operators are used to perform mathematical operations and numeric operands. This includes addition, subtraction, multiplication, division, and modulus operations. The commonly used arithmetical operators in Verilog are plus for addition, minus for subtraction, star for multiplication, slash for division, and percent for modulus or remainder. Let's understand this with examples. In the addition example, we add two 4-bit numbers a and b. Since addition can generate a carry, the result is y is declared as 5 bits wide. In the subtraction example, the result is simply the difference between a and b. In the multiplication example, the output width depends on the input widths. The result can be wider than the operands. In the modulus operation, the result is the remainder of division. In the division is example, any fractional part is truncated and only the integer value is stored. Some important rules to remember are operands must be numeric, the result width depends on the operands, and if x or x appears in the operands, the result becomes x. Arithmetical operators are commonly used in counters, addresses calculations, and data processing logic in Verilog. With this, we come to the end of the part 2 of the Verilog HDL course. In this session, we covered vectors, arrays, parameters, parameter overriding, and all the major Verilog operators with a clear examples. I hope this session helped you build a strong understanding of Verilog fundamentals. If you found this video useful, please like and share and subscribe to the VLSI Flow channel. If you have any doubts or questions, feel free to drop them in the comments. I will try to respond as soon as possible. Stay tuned for the next part where we will continue the more advanced Verilog concepts. Thank you for watching and happy learning.